Okay, this will be our last general study group session. We'll be covering electrical safety. And I ran across this ARRL PowerPoint and really didn't see anything that I could add by putting together my own presentation. So we'll just run through this and um, cover the topic. Safety, pretty straightforward, but it is critically important. And we'll just get started here. First thing to note for electrical safety when you're putting your shack together, you want to have a master station on-off switch. This could be, you need to plan this when you decide how you're going to power your system so that there is one point that you can get to, or somebody that's trying to help you if you have a problem get to and turn all the power off of the station. And you need to make sure your family knows where that power switch is and how to operate it, so that if you do get in trouble with something, they can at least get the power shut off so they aren't in danger when they try to help you out. So it seems like pretty much common sense, but it's something that can be overlooked, particularly if your station kind of grows on you. You just need to make sure you have that main power disconnect somewhere that's easy to get to. It's critically important not to work on live equipment unless absolutely necessary. And there's really about the only time I've worked on live equipment, the actual working wasn't doing anything to it other than testing it with probes, whether it be a voltmeter or an oscilloscope, something like that. But you definitely don't want to disconnect and reconnect wires and things like that, even though you think it's safe since it's only 110. But 110 volts is probably the most dangerous voltage you'll be working with, and you need to have a lot of respect for it. It's also important if you're doing measurements or probes or things like that, anytime you're working on an energized equipment, to have someone there with you, so that if there is an accident, they can at least help take care of you and get you the help you need. And kind of like firearms, never assume equipment is off or de-energized. Check it with a meter or tester first. Um, just because you throw a circuit breaker, you still probably ought to check things with a voltmeter to make sure it's off, because you don't know for sure what might have been done to that wiring that you're not aware of. And then if you're working on feed lines, you want to make sure that the transmitter is powered down, or the amplifier, if you have a secondary amplifier in the system. You don't want that thing to come on hot while you're working on the feed line or an antenna. It's good practice to keep one hand in your pocket while you're probing or testing energized equipment. I know early in my career, I did a lot of work around industrial power and control systems, and that was one thing wanted to make sure to do: keep one hand in the pocket, because it prevents you from completing a circuit through your chest, which is pretty can be very deadly. Wear shoes with an insulated sole, and remove the presentation said unnecessary jewelry, and I changed that to all jewelry. There's no reason to wear any jewelry while you're working on something. I'm not sure what necessary jewelry is. I know the first 10 years I was married, because of school and working in industry, I didn't wear a wedding ring. And then after I went into management and wasn't into working around the equipment like I had been, then I finally consented to wear a wedding ring. So hasn't been off since. And as I mentioned, most dangerous currents are those that go through the heart, arm to arm or arm to foot. And what that does is the current flow will disrupt your heart rhythm. And 60 hertz household current is extremely dangerous. It will penetrate the body easily and is a frequency that can disrupt the heart. So you don't want to give the current a path through your body if you can avoid it. Or even if you can't avoid it, just don't do it. A lot of guidelines come from the National Electrical Code on how you wire your home. There could also be some local building requirements. I do know there is in Pennsylvania, after electrical work is done, they send out an inspector to check on things. Recently, I installed a whole house surge suppression kit, or actually I had an electrician do it because the meter had to be pulled, and I haven't done that for a long time, and I figured there were rules about non-licensed electricians pulling meters, so I hired an electrician to do the wiring, and then it wasn't but a day or two after that, some little guy from the state showed up to inspect everything. And it's not a bad practice to have a licensed electrician perform or check the work. One of the reasons I like using an electrician, even though I can do a lot of this stuff, is at least I believe it safeguards your homeowner's insurance, so that if something happens, you can't be pointed to as the negligent source. So I don't know if that's in fact true or not, but that's just an opinion I have. There's some wire color standards or conventions that are typically used, where the hot wire has a black or red insulation. Black is the hot in a typical 120 volt, 60 hertz home power wiring. White is the neutral. When we're looking at DC power for the ham radio equipment, generally, almost without exception, the red is the plus DC voltage, the black is the ground. And then in the house wiring, the neutral wire has white insulation, and the ground wire has green insulation, or is a bare wire. And that bare wire or green wire needs to be connected to the bare copper terminal in a, say, a duplex outlet, or in the distribution panel where the circuit breakers are. If the equipment has a metal chassis, which a lot of it does, connect the ground wire terminal to the chassis. What that does is it makes sure that the chassis is at ground, so that if you happen to touch the chassis, you'll be at ground potential and won't get shocked from it. If you don't ground that chassis, what can happen, it can float, depending on how everything else is wired up, to pretty good voltage levels, where if you would happen to be grounded, say in your shack, and you touch the chassis, then you could be shocked there as well. You should always use 3-wire AC cords and plugs. Use cable and wire sufficiently rated for the expected current load. The units for current rating for wire is ampacity, and you can look that up on tables on the internet. And two most common sizes of house wiring are 12 gauge, American wire gauge, AWG, for a 20 amp circuit, and 14 gauge for 15 amp circuits. Now, if you start getting into installing an amplifier, where you get up into say a 1500 watt amplifier, you're going to have to, I'm going to pause here. Okay, I'm back. And we were talking about wiring an amplifier, and you get up into the max limit amplifiers of 1500 watts or 1200 watts and up in that range. and typically they're wired with a 220-volt supply and maybe a 30 amp circuit. So then you'll be looking at 10 gauge wire and 2-pole circuit breakers at 30 or 40 amps, depending on what the requirements for the amplifier might be. So that's another significant consideration if you're thinking about upgrading your shack to include a high power amplifier. Primarily, most homes are protected with circuit breakers. There's still places for fuses. Fuses need to be used for the voltage that they're rated with the recommended current rating. And you always want to put the fuse or circuit breaker in the hot side of the wire, never in the neutral wire. Opening the neutral doesn't remove the voltage from the equipment. If you look at a wiring diagram of 120 volt, 220 volt house system, you see where that makes sense, that just opening the neutral, you'll still have the 120 volts applied to whatever device is connected to the circuit breaker. There's safety interlocks. There's switches that prevent dangerous voltage when you open up some of the equipment. You need to be real careful disabling safety interlocks and make sure you really know what you're doing. It says never bypass an interlock during testing. Sometimes you have to, but then you just need to make sure that you're not anywhere near where the high voltage is when you're doing the testing. For example, if you wanted to put an oscilloscope, say on the power output of an amplifier, you want to shut everything down, disconnect the power to the amplifier, hook up the oscilloscope, and then turn everything back on, take your reading without touching any part of the probes for the oscilloscope. And then after you take your readings, shut it back down, and then you can disconnect your oscilloscope. Don't take shortcuts. Mother Nature's not very forgiving. There are ground fault circuit interrupters that you might be familiar with. Oftentimes they're outside outlets in your bathroom, and what they do is they detect an imbalance in the currents carried by the hot and neutral conductors, and if there's the slightest imbalance, they will open up and disconnect the power supply from the load. And the reason for that is if you do get a little disbalance, if you look at a circuit, 120 volt circuit, if the current in the black line should be equal to the current in the white line, and if it isn't, that means the current's flowing somewhere else, which is a bad condition. So then the ground fault interrupter will shut the breaker down. So if you've got moisture or direct earth contact with electrically powered equipment, it'd be a good place to use ground fault GFI breakers. Generators seem to be getting more and more common. You want to install it outdoors. You don't want to operate it in a closed space or a basement or a garage because the carbon monoxide from the internal combustion engine is deadly. So you need to also, if you're running it outside, make sure the generator isn't near open windows or doors because that exhaust can be drawn into the house that way. And it's a good idea to have a carbon monoxide detector alarms in your living and working areas. So for refueling, this may seem like common sense, but that's something that's not very common sometimes, particularly if you're in a hurry or in some sort of emergency situation. You need to turn the generator off while refueling. Use 2 people one with a fire extinguisher and the other one to do the refueling. Obviously, store the fuel well away from the generator and have a fire extinguisher near the generator, separate from the fuel. So if need be, you can get to it and take care of any problems that might come up. During portable operations, you should use a ground rod, install that connected to the generator. If you have one of these wheeled generators, that would be good to have. It's a little tricky connecting a generator to your home wiring system. It can be done. I've done it with a standalone generator I have. But the main thing to remember is that you need to just open up the main breaker coming into the breaker box that you're going to energize. Because what can happen is if you don't throw that, let's say you tie the generator into the circuit breaker box and backfeed it, that'll energize that box. If the main breaker is closed, then that means the power lines going out of your house are also energized, and that'll be feeding a transformer. And then the transformer will then be a step-up transformer. So then you'd be generating voltages of whatever the main power company voltage is coming into your house. And if somebody's working on that power line, trying to correct whatever's causing the power failure, it can electrocute them and kill them. So you have to be very, very careful and pay particular attention if you do backfeeding. Now, what I did is that I went through and I wrote a step-by-step startup and shutdown procedure and taped it into the circuit breaker box, so that if I needed to energize the generator to run the house, I know if I went through those steps, I wasn't going to miss anything. Don't leave it to memory, because you're liable to forget. Since then, I've installed a generator that has a transfer switch, and that way it's all automatic. The generator is constantly monitoring the AC power coming into the house. If it detects a loss of power for a set time, then it'll start the generator. It'll disconnect the main breaker, essentially disconnecting the house from the grid. And then once it's done that, then it'll connect the generator to the house circuit. So it's all done automatically, and then it'll repeat that sequence when the AC power comes back on the grid. So that's the better way to do it if you're going to use a generator for your house. Lightning protection. Best protections to disconnect all the cables outside the house, unplug equipment, power cords inside the house before a storm. You can get fires started from lightning on incoming feed lines and power lines. So that's your best choice. Should use grounding wires and straps as short and direct as possible to the ground rod. You should ground your towers, masts, and antenna mounts as well to your ground rod, and use mechanical clamps, brazing, or welding of the wires that you're connecting to the ground wire. Now, so that was pretty much covers the power in a radio station. Now we're going to look at the radio frequency exposure. And we covered this, I don't recall if it was in the general session or the technician session, maybe both. But this is just a review of that for the exposure limits. The thing to keep in mind is the two things that really contribute to exposure problems are the frequency of the RF power and the power density, how much power is actually interacting with the body. You remember this frequency here This was the allowable power uh, for controlled participant, which would be somebody that knows what the equipment's doing, like yourself or your family, and then the uncontrolled um, power levels are folks that aren't aware of the equipment, like your neighbors or passerbys or things like that. Um, this I got ahead of myself here a little bit. The two primary factors determine how much RF the body absorbs are the power density and the frequency. So the power density is the intensity of the RF energy. It's measured in milliwatts per cubic or square centimeters cubed. Um, and so, for an example, power density is 10 milliwatts per centimeter cube, and the area is 75 centimeters cubed. Then the total power is just multiplying those two values together for 750 milliwatts. The power density obviously is highest near the antennas in the direction in which the antennas have the most gain. So, for example, if you have a Yagi, that's a directional antenna that focuses the electromagnetic energy off the end of the antenna, that's where the highest power density is going to be. Increasing transmitter power increases power density, and increasing distance from an antenna lowers power density. And that all kind of makes sense if you think that through. Specific absorption rate is the rate the energy is absorbed from the power which the body is exposed, and the maximum permissible exposure level varies with frequency, as we talked about in some of the earlier graphs. Now, the FCC is going through something right now where they're changing the way these calculations and these studies are going to be made. And I really haven't seen anything definitive yet on what the new standards are going to be, but just keep an eye out for that as we go forward. And the RF energy is averaged over a fixed time interval. And we have controlled environments and uncontrolled environments, as I mentioned earlier. Primarily, the controlled environment's your home, and then uncontrolled is everything outside. And people in controlled environments are considered to be aware of the exposure, and those aren't outside. The uncontrolled aren't aware of the exposure, like your neighbors. Duty cycle plays a factor in the exposure, as the duty cycle is the amount of time that the power is on during the transmission. So, for example, 50% duty cycle is half off and half on. So lower transmission duty cycle permits greater short-term exposure because it averages out lower over the period of time that you're considering the measurement. And then this is just a little table out of the book showing the different types of modes that you might be operating and what the duty cycle might be. For example, you can see single sideband 20 to 40%. The voice FM, your handheld walkie-talkie, your FM base or mobile unit. When you're transmitting, it's 100% duty cycle because it's frequency modulation. The amplitude stays full on all the time, and what's changing to modulate the signal, if you recall, will be the frequency. So that's why FM is at 100%. And you can estimate the exposure, the amount of gain provided by your antenna, take into account the losses in your feed line, the gain of, I guess I already said that, gain of the antenna. And says all fixed amateur radio stations must evaluate their capability to cause RF exposure, no matter whether they use high power or low power. And routine evaluation must be performed at the transmitter peak envelope power and frequency within the FCC rule limits. Now, what they're saying is that you're required to perform the RF exposure evaluation, and there are forms that you can get offline at the ARRL and some other sites that you can do it, but only if your transmitter output power exceeds the levels shown for any band. So you can see here, this running here down to 10 meters is HF, and typically you run a 100 watt amplifier there, so you're well under that until you get down to 12, 10 meters. 6 meters, this is considered VHF and UHF. Typically those types of radios are at 50 watts, so you're at the limit. So it really becomes an issue when you start adding a supplemental amplifier, that you need to be aware of that. But it wouldn't be bad practice to find one of those forms on the internet and work your way through one. It's not that difficult. And 3 ways you could perform the evaluation is if you had an RF field strength meter, you could do direct measurements while transmitting to come up with your readings for the evaluation. You can use computer modeling if you're into doing that and have the capability. Or the easiest for most hams is just use the online calculator listed on the ARRL website. You must reevaluate the RF exposure for your station. Obviously, if you change to higher power, increase your antenna gain, say if you go from a dipole to a Yagi, or change your antenna height. If you lower your antenna, since the antenna will be closer to people, then the exposure will increase. So those are 3 conditions that would trigger an RF exposure reevaluation. You do not need to reevaluate the RF exposure if you reduce the output power of the station already in compliance. If the evaluation shows that your transmission exceed the maximum permissible energy limits, then you've got some knobs you can turn. You can reduce the antenna gain, you can reduce the average power level, move or rotate the antenna away from people. That would only be helpful if you had a directional antenna. Take measures to prevent excessive power from being radiated in your neighbor's direction. And there's, if you can get the antenna higher, farther away, that's always going to help in the exposure limits. Sometimes hams, particularly if there are restrictive homeowner association agreements, will put antennas indoors. They'll put them up in the attic of their house, some even in the room that they're transmitting from. And you want to make sure and go through the MPE evaluation if you're doing something like that, because you're a lot closer to the antenna than stations with external antennas. Place your mobile antennas on the vehicle roof or trunk to minimize exposure to passengers, and use speaker mic to reduce your exposure on a handheld. If you're talking on a handheld and holding it to your ear, that antenna is right up there by your head. And use a dummy load when you're testing the transmitter. Now, some notes on outdoor safety. And this is almost a no-brainer, but it needs to be said. Place all the antennas and feed lines well clear of power lines. If you think about what you're doing, you're taking a piece of very conductive material, the antenna element and feed line. And if you want to, if it gets in contact with another energy source, you're going to have a pretty serious shock. So stay away from the power systems. This is particularly something you need to pay attention to. For example, when we do Parks on the Air, I'm always setting up an antenna in a new location, and that's the first thing I need to look for is, are there any power lines around? Generally, you think of a state park as not having much in the way of a power grid, but you'd be surprised how much power they've got running around. So you have to make a survey of where you're going to put up a portable antenna, and make sure you're not too close to the power lines. And here's one of the general rules: no part of your antenna system should be closer than 10 feet from power lines. I like to keep it farther than that. At least 150% of the total height of the tower mast should be away from the power lines. So the more distance you can have, the better. But that's just something. The key thing there is to be aware that you need to check for it, because a lot of times on a portable setup, you're anxious to get things up and maybe in too much of a hurry. First thing you got to do is check for power lines. Then for installing antennas, you don't want to run feed lines over power lines or surface drops from a transformer to the house. If you're using trees to have your antenna and support lines go through it, remember power lines can be hidden in and around trees, and make a good thorough inspection of the installation before you start putting anything up. So people should not be able to come in contact with the antenna once it's installed. This can get a little tricky, particularly in an area like in a park. For example, we run a horizontal dipole about 5 feet off the ground, and so one of my jobs is to watch the antenna and make sure no one gets around there. And suggest you place a fence around a ground mounted antenna. That would be something like a tower. And then obviously read and understand the assembly directions thoroughly before starting. Excuse me. Tower mast is used to raise the antennas above buildings and other constructions. If the mast or tower requires guying, which are support wires to keep the tower from moving in the wind, keep all the lines and guys lines above the head height so people don't walk into them. If the guy anchors low to the ground, flag or fence a guy wire or the guy line. And it's kind of interesting. You don't notice guy wires, but next time you see, say, a commercial transmitter or a cell phone transmitter, look and see if you can find, see the guy wires. They're usually a pretty intricate support system for a tower. Building permits generally required for crank up and tilt over towers. I know in Treasure Lake, to put up a tower or an antenna, you need a permit to get started with the homeowners association. Comply with any applicable building codes, and towers should be grounded with separate 8-foot ground rods for each tower leg, with the ground rods bonded to the tower and each other. And if you're near an airport, you need to comply with the FCC and FAA rules. One of the most dangerous things I've seen in ham radio has been people climbing towers incorrectly. It's not uncommon to read of a ham that has a fatal or near fatal accident on a tower, and for the most part that's due to not using proper safety techniques and safety equipment. So if you're going to work on a tower, you need to have properly rated safety harnesses, hard hat, gloves, sunblock, and goggles. boots or work shoes to protect your feet, and enough crew to do the job safely. And everybody on the ground should also have a hard hat on. Um, the equipment that you would use, the safety harnesses, have life limits on them. And they're usually dated with an expiration date. So that would be one thing you'd want to check before you use a piece of safety equipment. And you need to run through the safety checklist before you're starting. Inspect your tower guide and support hardware. Crank up towers must be fully nested and blocked. Double check all the belts and lanyards for service life and capacity. That's probably a good excuse I can use for never going up to a tower. They probably don't have service belts at my capacity. Inspect all ropes and load-bearing hardware such as pulleys, secure and tag out all the electrical equipment. It's another activity that you don't want to be excited and try to do in a rush. Just go through the checklist and do what's safe, and you should be okay. And that's it for safety. This is the last video in our general class series, and I'll be posting it to YouTube here shortly. And remind everybody that if you have any questions, let me know, and we can do a quick Zoom meeting or email exchange or whatever's necessary to get things squared away. And the test is coming up shortly. I hope everybody's continued their studying and taking the practice test. I would think by the time you get to this point on your practice test, you should be fairly consistent in passing. If you're not and can identify those areas you're having a little trouble with, just let me know, or let someone else know that can help you out. And want to get you through this and get your general license so you can really start having fun with ham radio. So I guess I'll say 73. This is K3SKS and QRT. Thank you.